It is. All right, so welcome. So today we're going to continue talking about trusses, and we're going to put to use the matrix tools that we talked about last time, right? So matrix partitioning is something that we're going to see come into play in today's lecture, and that's also something that you're going to apply in the next homework. So homework 3, I'll talk about that later in class today. I just posted it on D2L. It's all about trusses, and it's going to be due a week from next Monday, so the 18th. So you have a little bit of extra time to complete it. That's also because it's a little bit of a longer assignment. So, so make sure that you give yourself plenty of time to get started, get your questions answered, and complete it before the deadline, right? So homework 2 due tonight. Any questions on that? Yes?
Oh, what's the best way to prove something stable? Like, can we look at it and say, oh, this would just move dynamically? Or do we have to do
Right. Yeah, so we haven't really, so far we've only discussed more intuitive ways to tell if something is stable, right? So there are a few things to look for. We talked about the geometric instability. So if you check, just do a mental check of your structure and say, all right, are the reactions concurrent at a point? If they are, then that's a red flag for instability, right? If they're not, then you're good on that end. And then but that's not the only thing to think about, right? Because you can have a scenario where, let's see, I have a marker measure. I actually do not. Well, I don't know if this will show up, but not too bad, right? So you can have a situation where here the reactions are not all concurrent, right, but they are all parallel. And intuitively you can see, well, if all the supports on this beam are rollers, there's nothing keeping it from moving in the x direction, right? So that's unstable. So looking for things like that, right? And then the other condition we talked about was, right, if you have a scenario like this, that's unstable, right? But if you have something like that, that's stable, right? Because now it's just technically a truss here. But if they're all aligned, right, then there's nothing to resist rotation, right? So look for those markers of instability, and if you don't find them, then that's a good indication that your structure is stable. And then, of course, the other check, right, is if NE is less than NR, then it's definitely unstable, right? No, I got that the other way around. If NE is greater than NR, right, then it's definitely unstable. So, yeah, so just kind of look at your structures like that. Make a decision, and then, for your work, you can just say it's stable, there aren't any indications of instability, or something like that. Right. Any other questions? Okay, good deal. It's going okay then? Everybody feels like they can get it done and submitted in time? All right, I do want to make sure everybody has a chance to fully understand, especially the load path problems. So, they aren't specifically, very lengthy or difficult, but it is a different thing that you haven't really encountered yet. So it might take a little bit more thought to get through it. All right. Okay. All right, so trusses then. I want to jump to our schedule real quick. All right, so the sections in the book that are noted as assigned reading, so really we kind of, right, Matrix Algebra 2, that was kind of a shorter lecture, so we already started talking about trusses, and technically the determinacy and stability is covered in these sections 5 and 6, which I put down here because we're not talking about stability until next week. But we did already talk about determinacy. So if you're looking for, in the textbook, information about truss determinacy, I think it's section 6 in chapter 7. Pretty sure that's the one that talks about determinacy. And then today's lecture is going to be focused on the information in section 9 of chapter 7. So that's going to be taking essentially a method of joints and applying matrix methods to solve it. So it's a cool technique, right? It allows us to speed up our calculations and also gives us a way to, evaluate multiple different load cases at the same time. So we'll get to that right off the bat. First, though, a quick overview of different methods of analysis for trusses. You're already familiar with method of sections and method of joints from statics. So just a quick recap, and we'll go over method of sections later next week as well. Method of sections is a technique that is best applied when you are looking for member forces of specific members within a truss. You're not trying to solve the whole truss. You just want to know what are a few of these members doing under a given load condition, all right? So that's a good time to use method of sections. When you do that, you want to make sure that you are strategic in how you select your cuts through the truss, right? And those cuts should only ever dissect members, all right? They should never go through joints. Sometimes you need to make more than one cut to find the force that you're after, but if you're, ideally you want to minimize the number of cuts and the number of equilibrium equations that you use when applying this method. But sometimes we can't avoid using more than one cut or more than one equation. So again, we'll look at a couple of examples next week on method of sections. Method of joints, that's the method that you would want to use when you're trying to find all the forces in the truss. And the method of joints is essentially the same as the method of sections. You're just making cuts so that you're isolating one joint at a time and you go through the whole truss, right? So you draw free body diagrams of each joint, and you have to start with one where there are only two unknowns so that you can work your way through. So, of course, since this approach is very systematic and it covers the whole truss, we can formulate it using matrix methods, and that's going to be our focus for today. There is a third approach that we'll look at later on in the semester, which is the finite element method. All right, so that's a separate set of lectures. And then there are other advanced methods for analyzing trusses as well that are not covered in this course. So just so that you're aware. Some of them are included in your textbook though. The textbook is a really great resource. We're certainly not using every chapter in this class, but there is a lot of material in there that I would consider applicable to maybe an advanced structural analysis course or advanced methods. So if structures is something that you're interested in, I highly recommend that you keep a copy of this book for reference throughout your career. All right, so now we're going to roll into our example where we're going to apply matrix methods for truss analysis. Again, this is covered in section 9 of chapter 7 in the book. And if you want a refresher on just the method of joints, that's section 7-8. All right, so the purpose of going through this process and applying matrix analysis to method of joints is so that we can analyze any possible set of loads on a given truss configuration, right? And we can also analyze multiple load cases at the same time, right? So up until now, you have successfully analyzed trusses for a given set of loads and a specific geometry and configuration for the truss, right? And you know how long that can take and how tedious it can be. And it can be very repetitive if you're saying like, okay, well, you just analyzed this one possible set of loads, but we have all these other load cases that we need to consider to design this truss, right? And we want to consider them all separately, not acting at the same time. So you don't want to have to go through that method of joints calculation for the whole truss for every single load case, right? So this will allow us to analyze all of those load cases. They're still analyzed separately, but they're analyzed at the same time in one go, right? So that's the point here. So the initial setup, and we're just using a very basic truss for this example, right? First, you want to label the joints if they aren't already labeled. And then you want to assume that all of the reactions are acting in the positive directions. So I'm going to highlight your reactions here, all right? So we're just going to make that assumption. And then you have at every joint, all right, every joint will have two external forces associated with it. So that's this point down here, all right? So the two external forces at each joint, one will be in the x direction and one will be in the y direction. And each of those forces will either be a reaction or an applied force. All right, so you know where the reactions are, that's determined by the supports. So wherever there's not a reaction, there's going to be an applied force or a possible applied force. All right, so that's your F2x, F2y, and F3x in this case. So in this setup, right, the reactions are all going to be considered unknown values for our analysis. The possible applied external forces will all be treated as known values, all right? Because we're going into this assuming that, you know, once we define load cases, we're going to know the values for these, okay? And then we also need to identify the internal member forces. All right, so that's going to be your F13. Well, I'll just highlight the arrows so that they're obvious, right? So you're going to have three internal forces to consider, all right? F12, F13, and F23. So those are your member forces, and we're going to assume initially that they're all in tension, meaning they're all going to be drawn in the positive direction. And for a truss, when we draw members in tension or compression, we consider how those internal member forces are affecting the joints, all right? So we draw a tension force acting away from the joints. So that's why the forces are shown like this. I find that, you know, sometimes that can be a little bit confusing. It's maybe counterintuitive because this sort of looks like you're pushing on the member, right? But think of it more as the member is pulling on the joints, right? And that's when the member is in tension. All right. Let's see. All right, so I covered everything up there. All right, so then the next step is to just go through systematically and write the equilibrium equations at each joint. So this is just the same process that you would do, you know, normally applying the method of joints, except now, right, just keep everything in terms of, you know, the generic numbered, you know, external force notations, internal force notations, reaction notations, right? So even if you know the values for your external forces, don't plug them in just yet, right? Keep everything in symbolic terms, and we are just relating these forces to each other through the truss geometry. So that's done through the equilibrium equations, right? Sum of forces in X and Y at each joint. And then once you've done that, now we have every equation, all right, because we have 2 equations per joint. Every equation includes one external force, exactly one external force, right? No more. So we want to rewrite or rearrange these equations so that the external forces are isolated on one side of the equation. All right, so you would do this for every single equation at each joint. And then you're ready to assemble it into a matrix form that will be conducive to our solution. So this is what this truss would look like in matrix form, where our rows, all right, so every row is one equation. Those represent the external forces. All right, and there's always going to be 2 times the number of joints rows, all right, so 2J rows. So I'm going to note the matrix size down here, 2J rows, and then for generic application, I'm going to up here make one more note, all right. Actually, it doesn't have to be up here. Well, it makes sense to put it up here. Okay. So because our goal is to analyze multiple separate load cases at the same time, right? I'm going to go ahead and call C, lowercase c, that's going to represent the number of load cases that we want to analyze. So the reason I made that note now is because down below, when I'm making a note of the dimensions of each of these matrices, all right, this left-hand side is going to always have 2J rows, and the number of columns is going to be however many load cases we're analyzing. So we're going to have C columns, all right? So right now, the way it's written, it just looks like one column. But once we bring in a bunch of load cases, we're going to expand that to however many load cases we have. All right, so as you can see, these external forces are a combination of known values, which are those external applied forces, and unknown values, which are the reactions. Now the columns in our matrix, all right, so the square, or it's not square now, but the coefficient matrix, all right, let's call it that. The coefficient matrix is representing the geometry of the truss, all right? That's where these values come from. The 1 over square root of 2, that's just your sine or cosine of 45 degrees in this case. That represents the truss geometry. And the columns of this coefficient matrix represent the internal forces. So whenever I write matrix problems in this class, I like to label the columns of the coefficient matrix, whatever that may be, according to what they're being multiplied by, right? So this whole column is multiplied by the internal force of member 1, 2, right? This whole column gets multiplied by the internal force of member 1, 3, and so on. So I just like to label those columns to help me keep track of that. All right. So all of these internal forces are unknown in our solution. The size of the coefficient matrix here is 2J rows and M columns, right? M being the number of members. The size of the column vector is M rows and C columns. All right, C being, again, the number of load cases. So this is just the initial setup. Now, the next step is to, in order to solve it, right, we want to apply matrix partitioning. So we're going to separate the reactions, which are the unknown external forces, from the applied loads, which are the known external forces, right? And so that's represented by these dashed lines here. In this case, the known forces are all grouped together. It doesn't really matter what order you write these equations in when you assemble your matrix, just as long as you make sure to, keep track of all the terms as you do that. So, since the reactions are all unknown, all right, and we have our first partition would be using the rows that have known forces. All right, so in this case, that would be rows 3, 4, and 5. So you're just taking those rows out of this matrix, all right? And since all of the columns are included, we still have all rows of the column vector there. And since 2j rows are what we started with, and as you know, we've defined R as the number of reactions. All right, then 2j minus R will be the number of rows in our first partition, since we're taking out all the reactions. All right, so we'll call the first partition A, as noted here, and the size of that first partition will be 2j minus R rows and M columns. And then we're going to have the column vector with M rows and C columns. And then our external force matrix will have 2j minus R rows and C columns. Yes. I'm going to replace those with a traditional cross there. Now, for a determinate truss, 2j minus R is equal to M, right? And since we started out with a determinate truss, we have a square first partition, all right? So I'll note that this first partition is square. So then the second partition are just the rows that we left behind after the first, right? So those are the rows that have the unknown forces, in this case 1, 2, and 6. And we'll call that second partition B. The sizes, dimensions of these matrices, all right? So matrix B will always have R rows and m columns, so r by m, and that's not necessarily square, right? In this example, it happens to be square because those are the same, r and m have the same value, but it doesn't need to be. We still have m by c for the internal force matrix, and r by c will be the result. All right, so I already talked about how that first partition should be square. It also should be invertible in order for us to solve. You have a question? Oh, okay. So what it means if it's square, right, as we talked about, is that just means that it's determinate. If it's invertible, that means that it's stable. All right, so if it meets those criteria, then we can solve for the unknown internal forces using this formula. Now, a couple of notes here, and we'll come back to this when we talk about stability next week. So I'll just say, all right, it just follows from what we talked about up here, right? If the first partition is not square, it's either indeterminate or unstable. And if it is square, but cannot be inverted, that means it's unstable. That's true for the first partition, right? So for the first partition of the coefficient matrix, yeah. I'm not sure I follow your question. For the reaction forces.
Well, I was thinking of like a situation if there was 2 pins instead of a pin and a roller.
Sorry, say that again.
If there was 2 pins instead of a pin and a roller, there would be 4 reaction forces.
I understand. Okay. Yeah. So if there were 4 reaction forces in this truss, then we would end up with a first partition that is not square, right? And it would be indeterminate. So in that case, your first partition would have more columns than rows, right? So you'd have more members than known forces. Yeah. So for, any problems that you are asked to use this method to solve, I promise the truss will be determinate and stable. All right, I'm not going to expect you to try and attempt to solve a truss that's not going to work out with this method. This method can only work with determinate and stable trusses. So, so you can count on any truss being determinate and stable if you're asked to use this method to solve it. However, you should understand the implications of, right, what happens if one of these conditions occurs, right? If it's not square or square but not invertible, what does that mean, right? All right, any other questions so far? All right, so now we get to actually use this system that we've set up, All right, so the next stage is to bring in some values. We define a set of load cases. All right, so now we know what forces are being applied, exactly the values and the directions and where. So here are the given 4 load cases for this truss that we're going to consider. So our value for C is 4. We're going to have 4 columns in our external force matrix and our internal force matrix, all right? So we are going to first write out our external force matrix. These are the known applied forces, and I'm going to label each column according to the load case. So the first load case, we have F2x is positive 1,000, and then there are no forces applied anywhere else, so the other 2 are going to be 0, right? For load case 2, we just have F2y, so F2x will be 0, F2y is negative 1,000, and then F3x is 0. For load case 3, we have all 3 loads, all 3 possible applied loads have a value, right? So F2x is 500, F2y is negative 500, and F3x is positive 500. And then the last load case only has F3x. So the first 2 entries are 0. And then we have 1,000 in the last row. So the size of this matrix, as you can see, we have M rows and C columns. All right, and that M is, I know it doesn't fully make sense, like, well, why would that be M? It's because it's determinate, remember, right? It's 2J minus R is really where that comes from. Because we started off with 2J rows, and then we took out all the unknowns, which are the reactions, right? So what we're left with is M because it's determinate. All right, so then if we take that square and invertible first partition, invert it, pre-multiply both sides of that equation. Now we know, oops. All right, so we know values for this matrix, so we plug that 3 by 4 in. So now we're multiplying, we're taking a 3 by 3, and we're multiplying it by a 3 by 4. So our result is going to be a 3 by 4. So then each column in our result is going to represent the internal forces for each load case respectively. So for the first load case, we have 707 pounds in tension for F12, 500 pounds in tension for F13, and 707 pounds in compression for F23. All right, so positive, we assumed positive in the beginning, so positive results confirm tension. Any negative result indicates compression. For load case 2, we would get negative 707, positive 500, and negative 707. For load case 3, we would have 0, 1,000, and negative 707. And then for load case 4, we would get 0, 1,000, and 0. Now that we know the internal forces, all right, we take those and we plug them into our second partition equation. right? So since we have our second partition is a 3 by 3 in this example, and we're multiplying that by a 3 by 4, our result is going to be a 3 by 4. And what we get are the reaction forces for each load case. All right, so first load case, we'd have negative 1,000 is R1X, negative 500 is R1Y, and positive 500 is R3Y. For load case 2, we would have 0, 500, 500. For load case 3, negative 1,000, 0, and 500. And for load case 4, negative 1,000, 0, and 0. Right. Questions? So I highly recommend using Excel, right? You already went through that in homework 1. Watch those short videos on how to deal with matrices in Excel. That would be a great tool to use for homework 3 when you're solving a truss this way. I don't recommend using your calculator just because with larger trusses, larger matrices, it can be more frustrating than it needs to be, right? With Excel, you can lay out your matrices and you can see the whole process, right, in one sheet. If you make a mistake, and every time I go through this myself, I always catch some little thing that I typed in incorrectly or translated incorrectly, right? So I would be surprised if anybody got this right in the very first go of inputting it into a calculator or an Excel spreadsheet. With Excel, you can see everything and then you can go through, and if something doesn't look right in your results or isn't working out, you can go, okay, where did I get something wrong? Like, where did I make a mistake? And it's easy to update that, right? And it'll automatically update your results rather than having to type things into your calculator all over again. So I highly, highly recommend using Excel for this.
Does just taking a screenshot of that work for showing your calculations?
Great question. So in the assignment problem statement, I explain what I want to see with your submission. So you're welcome to submit a screenshot of your Excel spreadsheet, but what I'm going to be looking for is basically writing out the matrices similar to what's written in this example. Again, you don't have to write the actual matrix computations, but writing the matrix equations, similar to this, and then the results out. Yeah. So that's what I'm looking for in your homework assignment. And then also summarizing your results with sketches, right? So just like this here, for each load case, include whatever loads are applied, right? The reaction forces and the internal member forces. So there are a couple ways that you can go about representing those internal forces. One is using the arrows, as I described earlier, right, where tension shows the arrows acting away from the joints and compression shows the arrows acting towards the joints. Or you can note it simply, this is on the next page actually, you can use this method too, right? So you can just write the value and then compression for C for compression or T for tension in parentheses. Either way is completely acceptable. Just make sure that you include the applied loads and also the reaction forces. It's not shown in these examples, but right, as shown here, that's what you're solving for. Another note, right, on this approach, it can be tempting because what we normally do when we solve problems is find the reactions first, right, using statics. solve for the reactions first and then go through and find the internal member forces. So you'll note that with this method, we're reversing that order. We're finding the internal member forces first and then solving for the reactions last. So in this, in your assignment, what I'm asking you to do is to follow that method, right? So don't try to find the reaction forces first. That's a common mistake that students might make, is solving for the reaction forces first and then treating those reaction forces as knowns. That will mess up the whole process, right? Number one, your reaction forces are going to change for every load case. So you're essentially repeating the solution 4 times, which the whole point of this was to just do it once, right? Set everything up in general terms, and then you can solve for any load case and multiple load cases at the same time. So then what your homework assignment will ask you to do is to, after you've completed the solution, all right, pick one of your load cases and apply those equilibrium equations to check, to verify that the external reactions you got from your solution are correct, right? So that's what that will look like. Yes?
On our homeworks, do you want us to write out the equilibrium at each joint like we did in this example first, or?
Yeah, so write out the joint equilibrium equations, all right, and then from there you can show the matrix assembly, right? Yeah, so you don't necessarily need to show the intermediate step of rearranging the equations, right? Yeah. All right, any other questions? Okay. All right, so we covered, oh, yes, question?
Couldn't there be external, like, loads or forces on the same, like, planes as those reaction forces? Because, like, at the top, we only drew them. Like, you keep going up.
Oh, up here?
That.
Mm-hmm.
Like, we only drew those external forces on the spots where there were, like, gaps from reaction forces.
Mm-hmm.
Why couldn't there be, like, an external force at, like, number 1?
I understand your question. So why wouldn't we put external forces here and here potentially? So yeah, so technically, yeah, a force could be applied there, but it's not going to affect the truss at all, right? Because it's just going to go straight into the support, right?
But
So
wouldn't it affect the reaction?
it would affect the reaction, yeah, but it's not, that's, when we go through analyses like this, that's not something that we worry about, right? So if there was some other external force going into this reaction, it would be from a separate system, and we would just, right, we could add that, whatever that value was, directly to this value, right? Yeah, but yeah, you don't have to worry about that for this system, and in order for this process to work, we need to make sure that we only treat we only assign 2 forces at each joint, right? And one will be reaction force, one will be applied external force. Yeah. Or I should say, one will be X, one will be Y, and either one will be either a reaction or an applied force. You can't have both at a given direction. Okay. Yeah. Any other questions? All right, so with a few minutes left, we'll just touch on this cross-bracing note, and then I'll show you the homework assignment. So here, we talked about this a little bit, right, at the beginning of the semester. If you have a truss panel like this, where you have cross diagonals, if those cross diagonals are both light relative to the other members, all right, and have negligible compression capacity but substantial tension capacity, that would indicate that you're dealing with a cable or a tie, right, a tension-only member. So we would treat one of them as being engaged in tension and the other one would be in slack or compression for a given load case or a given load condition. All right, so if we consider an applied force acting downward, all right, and we were to cut the panel like this, if we drew a free body diagram of the right side of the cut, we would expose 4 internal forces, right? But with a load, an external load in the downward direction, we should be able to readily tell which one of those cross diagonals is active. So which one in this scenario is going to be active in tension to resist that downward load? Can you tell?
The bottom one.
Right, yeah, the bottom one, right? Because it's the only force in this panel that has a vertical component to it. If you had another member, like if one of these members happened to be sloped in a upward manner, then you could, it's possible that this member would also be zero force, like both of these would be inactive, but that's not something that you'll encounter in this class. So you've got one that's going to be active in tension, and then this one is going to be in slack, right? In other words, it's a zero force member. And then, of course, if you reverse the direction of the load, that would switch, right? You'd have the top one in tension and the bottom one would be in slack. So the useful thing with knowing this is that if you recognize which one is inactive, then you can ignore that member for your analysis. And so that way, a truss that appears to be indeterminate will become determinate for purposes of analysis for that given load case, right? And the method of sections that we just applied here is usually the best approach to determining which member is going to be active and which one isn't. All right, so we'll look at that more in an example next week, but here I'll just show you the homework assignment. So this is the truss you're going to analyze. It has 5 joints, so your matrix, how many rows do you think your matrix will have? Remember, it's the whole matrix, the whole truss. So we start off with 2 equations at each joint, right? So 2J rows, 2J equations. And then once we separate out the partitions, that's when it'll whittle down to 7. Yeah. All right, so the directions talk you through the process. Follow the example. That goes through all the steps as well. And the load cases that you're given in this assignment, you have 3 load cases. So the first 2 are established for you, and then the third one you get to define your own. So a bit of a choose your own adventure assignment. There are just a couple of requirements, right? So you have to have at least 2 different joints with at least 1 non-zero applied load on it. So that's an opportunity to just kind of play around, explore, see how this truss will respond to a given load case. The rest of the assignment is going to be stuff that we really talk about next week. So we'll talk about that later. But if you wanted to get a jump start, you could get going on this first problem, which is going to be the one that probably takes the most time, all right? Okay. Any questions? All right, well, thank you all for your attention, and I will see you on Monday. Have a great weekend.